Today's topic is electromagnetic induction. Why electromagnetic? Because magnetism and electricity, they interact with each other and gives rise to certain phenomena that we are going to study today. Let's study flux. We have already seen flux when we are studying electricity. Now, we have flux, magnetic flux as well. Today, we are more interested in magnetic flux rather than electric flux. What is magnetic flux? If you take a loop, let us say you attach a galvanometer in this loop, so to make it better. This galvanometer will not show any reading, nothing has happened. Now what you do is, you take a bar magnet and bring it close to the loop. What will happen? The magnet generates some lines of force, magnetic force. Which gives rise to a magnetic field. And if this magnetic field is changing, then you will see some deflection in the galvanometer. So when we talk about flux, flux is something like a bundle of lines of force that is coming out of a surface or a loop, closed area. And if their number or strength changes with time, then you generate what is called EMF. And this is what Faraday's law is. What Faraday's law says is that if you have a closed surface, like a closed loop, and if the magnetic flux through it is varying with time, then an EMF is generated in the loop. And how it is related? It is related like this. You have a flux, which is defined as B dot ds, which is a dot product of B and S. B we know is simple to find out wherever it is. And how do you find the direction of S? For example, if you take a loop, if this is a loop in which you have current I flowing through it, then what you do is, first of all, ds at any point is always perpendicular to the surface. Okay, it is perpendicular, but which way? The perpendicular can go this way or this way. All right. So what you do is, to find it, you use right hand rule. What this rule says is, you take your right hand, curl your fingers, draw a better diagram here. This is the current. Curl your fingers in this direction. Then the thumb will give the direction of ds. Once again, take your right hand, curl your fingers in the same direction as the current. The thumb will give you direction of ds. Now the direction of ds can keep changing from place to place. So you have to be careful as to find out the correct direction of ds. But in many geometrical shapes, ds is not very difficult to find. Mathematically, the flux, this lines of force or the bundle of lines of magnetic force, magnetic lines of force, a bundle which is coming out of a surface is a dot product of magnetic field. B is magnetic field in a small area multiplied by that small area and dot product of these two. If you integrate all these areas over the whole surface, what you will get is flux, total magnetic flux. So the flux can be changed, increased either by increased, or the flux can be changed either by changing the strength of the magnetic field or changing the area or changing the direction between the two. Any of these will change the amount of flux coming through a closed loop. All right. Once we define our flux in this fashion, Faraday's laws of magnetic induction says that if this flux is changing, then an EMF is generated, which is equal to negative of the rate of change of flux. This is principally Faraday's laws of magnetic induction, which says that through a closed surface or a loop, if the magnetic flux changes, it gives rise to an EMF. An EMF is generated. As we saw, once this flux is changing, this galvanometer starts showing reading. And if we stop moving this magnet, the galvanometer reading will again go back to zero because d phi by dx dt becomes zero. So to generate EMF, the flux has to keep changing with time. Now let us assume we have an area wherein we have magnetic field. Then what you do is you take a conductor of say length L and move it with a velocity v. This conductor L, this conductor is in a magnetic field which is perpendicular to it. And then you move your conductor perpendicular to the length of the conductor. Then again EMF is generated. If I call it and PQ, an EMF will be generated across length PQ, and this will be equal to B times velocity into and I will be earlier we saw that to generate EMF, you had to have a loop. No, it is not necessary. You can generate EMF in a structure which is not a loop structure also. In this case, what happens is this conductor is cutting through the flux, through the magnetic field, and hence cutting the flux. And B is constant. When we are moving this conductor in this field, when this conductor moves in this field in this direction, then what happens is that this conductor is sweeping some area. Sweeping some area meaning it is crossing across the flux. And what is the area that it is creating every time interval is VL, because L is the length, V is the with V velocity, it would cover so much of area. So B is this B, and the area that it would cover is so much. And since this is per unit time, so EMF generated is BVA. This is the EMF. If the resistance of the loop is or conductor is R, then there will be current setup if this was connected in a loop in some way. If it is not connected in a loop somewhere, current will not be set up, but you still have the EMF across the conductor. Okay. In our case, when we were talking about this conductor moving in a magnetic field, this EMF is generated on account of electric field being set up in the conductor. Integrate over the loop. This is equal to so this d phi by dt will give rise to generate an electric field within the this electric field will be generated within the conductor. Another is Lenz's law. Again, we take this example of a loop. You bring a magnet towards it. Let us say if this was North Pole, then what will happen? If you see along the direction of the magnet, this phase will become North Pole. Why? North Pole will repel North Pole. That is what it is. Lenz's law says that direction of induced current is such that it opposes the change that caused it. What it says is that Lenz basically says, don't disturb me. If you disturb me, I will behave in a way that this disturbance is minimized. I will act opposite to what external forces do. This is what Lenz says. So if you move a North Pole towards the loop, and if you see the face of the loop along the magnet, this face will also be negative. Why? Because when this becomes negative, it repels the movement of this magnet. It says, don't come close to me, stay away from me. And this is only possible when it tries to repel it. This is basically what Lenz's law is. Next, we talk about self-induction. What is self-induction? Again, we take a loop. If we established current through it, and we know if current is passing in a loop, then magnetic field is generated. All right. And obviously, if magnetic field is generated, magnetic flux will also will be generated. This magnetic flux is related to B, and B is in turn related to I. Now, what if I is changed? If I is changed, B will change. If B changes, magnetic flux will change. So we have a case of by dt, changing magnetic flux. And what it will do? We have already seen that if you have a case of changing magnetic field, an EMF is generated. So an EMF will be generated within the loop by way of changing in the current in the same loop. Isn't it funny? You have a current in a loop, and if the loop current is changed, there's an EMF generated within the loop. And this EMF this is generated, it is on account of self-induction. Okay. Now, let's define some terms. Y is equal to Y is equal to Li. If you have any loop, object, or any coil, whatever, if it has an inductance, then the flux through it is given by this formula. So EMF is minus d phi by dt is equal to, if we use this formula, this we also know phi is equal to v dot ds, integrating the whole surface. This will imply d phi by dt is equal to and d phi by dt is equal to this was if the coil had single turn. If you have n number of turns, then this simply gets multiplied by Okay. Now, if we talk about solenoid, what happens there is, in a solenoid, we know B is given as N mu naught, where N is the number of turns per unit length. Okay, and we also know that in a solenoid, if this is the loop surface, ds is always perpendicular to B. So our d phi by dt becomes B is constant all along into area. Area is equal to pi r square. This becomes, substitute the value of B. Now we go to this N is total number of turns, and if we can replace it with number of turns per unit length into the length, then let's take out the constant part out first. N into N again, mu naught pi r square. Then we are left with d by dt. And this was d by dt. So if we rearrange, this becomes mu naught L square, mu naught L square L. Now, if you compare this expression vis-a-vis this expression, so this is our, if you take minus sign, this is your EMF. Then this portion is our mutual inductance. This portion. So our L is mu naught L square L pi r square in case of a solenoid, where N is the number of turns per unit length, and we are talking only, this is the length of the solenoid. This is the radius of the solenoid. So a solenoid is an equivalent of, the equivalent of inductor for a solenoid is given by this expression. This is the expression for equivalent inductance of a solenoid. Now, next topic we come to is, we have seen a solenoid can behave like an inductor. So let's do some more exercise on the nature of inductor. Inductor is basically a coil, and let us analyze it in a LR circuit. This is the inductor. This is the inductor. This is the resistor, and this is the battery. We connect EMF to it. Now, when you connect the battery, what happens is E minus L a current will be established inside this, which is given by this formula. What is this? This is the voltage across inductor. So out of E, so much of voltage will be dropped across this, and what will be left is this much. This voltage is available to R, and which will be equal to R into I. Now, if you take this expression, this is a differential equation. If we solve this differential equation, what we will get is that I is given by this expression says I at any time t in this loop is given by EMF of the battery that you have connected divided by the resistance, and R is the resistance, L is the inductance. And if you plot it, this graph with this to time, as the time goes by, as the rate is very high, and then finally it becomes equal to asymptotic, and the asymptotic value is E by R. So this is exponential rise, and then it levels off. Now, what if we already have a coil which we charged earlier, and through R, we simply short it. If we do this, then what happens is, this is the voltage which is across L. The same voltage is available to R. And if we say this is the current I, and this is the differential equation that we get in case of discharging of LR circuit. Now, the expression that we get out of this differential equation will be I is given by I naught e to the power minus t. And if we plot it, time versus I, then what happens? It starts with some value and it decays. And this value, which is started, is I naught. And by the way, if you had charged this in the previous loop, then I naught would have been E by R. This is the initial current. At t is equal to 0. So the discharge will be an exponential decay. Now next we come to is when we pass electricity through a coil, the coil retains charge. We have seen this, where have we seen this phenomenon earlier? In case of capacitors. Capacitor is a device which stores charges, and so is an inductor. So how much energy is stored in an inductor? Let's see. We know EMF is equal to is also equal to R. So this is we come to our charging circuit. In charging circuit, this is the voltage which is consumed by L, and what is left is E minus LDR by dt for the resistor. So we have E LDR by dt is dropped across the inductor, and this is the voltage which is left for the resistor. Now what we do is this is also same as EI dt minus Li di I square R, just a mathematical manipulation. Dt we multiply by both sides, and also we multiply by I, both sides. Now what you see is, if you see this expression, this is nothing but what we do is we integrate all the expressions. So this becomes this is also minus I is just final line. So let it be like this one. What is this? EMF multiplied by total charge. So this is energy supplied by battery this is energy obtained by inductor and this is energy consumed by resistors. We have studied earlier that power consumption by resistor is this was when I was constant. In this case, I is not constant, so we integrate I square over the total time. So if you look at this expression, the energy stored in inductor is Li square by 2. Similarly, can we find out energy stored in a solenoid? Why not? We have already seen magnetic energy is equal to Li square by 2. And we had earlier, we had got an expression for mutual inductance for a solenoid. So taking this value from here and putting in this equation, it will become mu0 n square pi mu0 n square pi square. This is equal to, now what we do is, what is this equal to? This is nothing but volume of solenoid. So can we write it that magnetic energy I square by 2 into mu0 n square. This is volume. Okay. And if you can rewrite it, yeah, we have a reason to arrange it like this, and which is that this expression is nothing but magnetic field in a solenoid. So we can write this as V square V. And if we define magnetic density, magnetic energy density, which is magnetic energy per unit volume, then this becomes magnetic density is equal to magnetic field divided by 2 mu naught. Okay. Now let's study some expressions for mutual induction. You take this coil, here. If you pass current through A, magnetic field will be generated in this. Now this magnetic field will cross through another coil which is kept near it. This will, you can say this is B1, this could be B2. This will be magnetic field nevertheless, which is on account of, while we will have magnetic field on account of coil A. Okay. Then we can say flux through B is equal to we know that flux in this second loop which is induced is on account of flux of which is generated in loop A, and this flux is proportional to I. So if we write a mathematical equation like this, in which this flux is a factor of a linear to magnetic current in this loop, then this constant of proportionality is mutual inductance. Which purely depends upon it's purely a geometrical constant. Okay. Now, since this is a flux, we can define through B, and this is given by F. So we can define EMF that is generated in this loop is equal to mutual inductance time rate of change of current in this particular loop. So M is defined mutual inductance or self-inductance, both same thing. Now let us take two cases of mutual inductance. We take this loop, and then what we do is we have another loop around it. Okay. And then what we do is We connect a battery. Now what will happen? The moment we connect a battery, magnetic field will be generated in the inner loop, which will be within the solenoid and not outside. Outside, this here or here, B will be 0. Okay. So if we call this as coil A, this as coil B, on account of coil A, coil B will get induced current or induced EMF, but the flux through coil B will be limited to the flux of this. And what is the flux of this? The flux through B will be same as flux through A. Provided both had same number of turns. So if we do the analysis from magnetic field point of view, what we get is, let's not say this to start with. What we have to keep in mind is that when we are trying to find flux through this coil B, which is the red one, there will be no flux in this region on account of coil A. Okay. So magnetic field in A, we know is an A mu naught A into area of A. This is this, and if you flux through A is, this is the magnetic field into area. This is the magnetic field within a solenoid, and this is the area, which will be equal to number of turns per unit length, current through area into right. Now what is the flux through B? Flux through B will be purely on account of this only. And mind it, this flux is going in every coil. So what we'll have is, let us say the coil B has n number of turns. So this will be simply nothing but, or you can say this is where L is the length of coil B. Now, if we, for example, if we wind one coil over the other, then it is not necessary that you have to wind it all the way on the same length as the inner coil or the outer coil. Both lengths could be different. If this length happens to be L, then total number of coils you can replace by number of coils per unit length for B into A. This is the expression. Now take the other case. What would happen if instead of passing electricity here, we were passing electricity in this loop? Then what would happen? Then since this coil is very well within the red coil, there will be no restriction as to there is some area where there is no magnetic field. It will have full magnetic field as coil B. So this exercise was basically to distinguish that in case an inner coil is energized or the outer coil is energized, the mutual inductance, the treatment are different. Now this time what we do is, there are two coils. Coil A is the black one, coil B is the red one. And now we energize the outer coil. Once the outer coil is energized, whatever magnetic field is generated within the outer coil, coil A will have the full same, will share the same magnetic field. So the flux through coil A is defined as flux through B. Now this flux B is going through each turn of coil A. So we multiply it with number of turns in A. This number of turns A can be replaced by number of turns per unit length into L. If we take L as the length of this coil, and flux through B, flux through this coil is, this is B times. Now flux through B is a small correction. This will not be so. Flux through A is defined as total number of turns in A multiplied by the magnetic field through it. This magnetic field through it, through coil A, will be same as magnetic field through B, because there is no restriction. So magnetic field will be same as what was in coil B and its own area. Now this factor becomes this factor. Total number of coils is equal to number of coils per unit length into its own length. This magnetic field is the same as coil B, is this magnetic field, and area of this its own coil is so much. So you see the difference between the two. In this case, the flux was limited on account of magnetic field not being here, but that is not the case in this. So these two things you have to keep in mind.